So the dot product, multiplying two vectors together gives us a scalar, and it's known as the scalar product. Now we're going to look at the cross product, and the cross product gives you a vector. So we'll end up with something that we have coordinates for, which is a directed line segment from the origin to that point. So this is also known as the vector product. So the cross product is going to give you a vector, and it gives a very specific vector. It gives you a vector that's perpendicular to both vectors, A and B, that you're taking the cross product of. Now, here's the thing. This is not associative because A cross B is not equal to B cross A. We're not getting a scalar in this case or just a number. We're getting a directed vector. And what happens is if you change the order of crossing, if I do A cross B, I'm going one way. If I do B cross A, I'm turning or going the other way. So it ends up being the opposite. The vectors will have the same magnitude, but they will be in opposite directions. So this is the anti-associative law, that it does matter if you switch order, and switching the order in which you take the cross product will give you a vector with a different direction. But it still will be perpendicular. It doesn't matter which way you do, A cross B or B cross A, the resulting vector will be perpendicular to both A and B. So there's this formula, A2B3 minus A3B2. That's the x-coordinate. The y is A3B1 minus A1B3. And then the z-coordinate would be A1B2 subtract A2B1. I don't want you to panic about memorizing this because as mentioned in the content, there is a trick, and I'm going to show you how to do that. So by using this formula or the trick, you get a vector. So you're going to get an ordered triplet with an x, y, and z. That'll be the location of the endpoint of your vector. Now, if you are just interested in how big the cross product is, so not necessarily as a vector, you just want the magnitude or the size of it, you can use a formula that's very similar to the one for the dot product, except now it uses sign. So the magnitude of A cross B is the magnitude of A times the magnitude of B times the sine of theta, where theta is in between. Because this is a magnitude, it gives us a scalar. So cross product gives you a vector, but the magnitude of the cross product, you can either do the magnitude of this or you can use this formula. When we get into the applications in the next section, you'll see when it's useful to use this formula. So we're going to find a vector that's perpendicular to 1, 3, 2 and 4, negative 6, 7. And then we're going to verify that the resulting vector is perpendicular to both of those. So I'm going to let this be A and this be B. So I'm trying to find A cross B. I could start filling in this formula because the x would be the 1, that would be the 2, that would be the 3. But again, I promised you a trick, and this is how the trick works. And the trick just fills this in without having to remember the order of the numbers. You're going to take your first vector, and you're going to write it out twice right after each other. So I go 1, 3, 2, 1, 3, 2. I'm going to take the second vector, and I'm going to do the same thing underneath. 4, negative 6, 7, 4, negative 6, 7. Okay, and order is important. If we're doing A cross B, I'm going to put A on top, B on the bottom. They just said find a vector perpendicular, so it doesn't really matter which order I do it, but I'm going to do this one first and that one second. So after you write them out twice, you're going to cross off the first column and the last column. And now it's going to be x's. You're going to do 3 times 7, subtract 2 times negative 6. So I do 3 times 7, subtract 2 times negative 6. That's going to be the x part of my cross product. So that's going to be 21 plus 12, or 33. Now I'm going to move over, and I'm going to make an x here, and this is going to be my y product. So I'm going to do 2 times 4, subtract, it's always subtract in the middle, 1 times 7. So I do this diagonal, subtract that diagonal. And that's filling in A3B1 minus A1B3. So that's going to give me 8 minus 7, which is going to give me 1. So the y part is 1. I'm going to move over to my last set of 4 to find my z. So I do 1 times negative 6, always subtract 3 times 4. So that's going to be negative 6, subtract 12, or negative 18. So this vector is the cross product of A and B. Now they wanted to verify that the resulting vector is perpendicular to both. Well, hopefully, so I'm going to call this R for my resultant. If R is perpendicular to A, from the last section we talked about, that gives a dot product of 0. If the dot product is 0 and neither of the vectors is the 0 vector, it means the two vectors are perpendicular. So that also means that R dot B should equal 0 as well. So I'm going to do that one first. I'm going to do 33, 1, negative 18, and I'm going to dot it with 1, 3, 2. I'm going to use the trick for dot product that puts the coordinates together. So 33 times 1 is 33, plus 1 times 3 is 3, plus negative 18 times 2 is negative 36, which gives me 0, and that means R is perpendicular to A. Now I'm going to check to see if it's perpendicular to B by again doing R, which is 31, 1, negative 18, and dotting it with 4, negative 6, 7, and seeing what happens. So 33 times 4 is going to be 132. I'm just going to verify that. Yep. 1 times negative 6 is negative 6, and negative 18 times 7 is negative 126. I put those together, I do indeed get 0. If the dot product of two non-zero vectors is 0, then the vectors are perpendicular. So the dot product equals 0 means perpendicular, and the dot product gives you a scalar or a number. The cross product gives you a vector, and the vector you get is perpendicular to both. Dot product, it doesn't matter what order you do it. We did A cross B, and we got 33, 1, negative 18. If you did B cross A, I would get the exact same vector, but going in the opposite direction. You can verify that if you want to by putting B on top, A on the bottom, but A cross B is not equal to B cross A. We get opposite vectors. They're going in the different direction. And when we talk about torque in the application section, that will probably make a little bit more sense.